Welcome, everybody. It's our pleasure to welcome you to the first round of the afternoon presentations of our conference here. It's my pleasure to welcome Alex Gilbert from the Colorado School of Mines and the Payne Institute. Alex is a complex systems researcher focusing on climate policy, energy markets, nuclear innovation, and space resources production. He's a project manager at the Nuclear Innovation Alliance, where he improves federal policy and regulations to commercialize advanced nuclear reactors to mitigate climate change. Beyond his work at NIA, Alex is pursuing a PhD in space resources at the Colorado School of Mines, where he focuses on resource governance, environmental protection, and space nuclear power. He's also a fellow at the Payne Institute for Public Policy at the Colorado School of Mines on research related to energy, environment, and outer space governance. Alex is adjunct faculty at Johns Hopkins University, where he co-teaches a course on nuclear power technology and regulation. And he's going to speak to us today about nuclear fuel cycle for Mars. Welcome, Alex.
Thanks very much for that introduction, Lee. And thanks for joining today. I've found the presentation so far to be really interesting. I hope that you will gain something from this presentation in terms of understanding why nuclear power is a very potent and useful technology for us to use on Mars, to understand a bit about how the fuel cycle issues on Earth affect our choices in outer space, and also to understand how we might be able to develop a fuel cycle on Mars itself. So to begin, I really want to start with just a basic question. Why do we want to have nuclear on Mars? It's a relatively simple answer, and it's just that it is a really effective technology that can complement or replace solar power or other sources of energy almost completely. The energy density of nuclear power is very high, which is something that is advantageous when we're talking about the high delta V and launch cost to get to Mars. The reliability characteristics of nuclear power are very high. It is dispatchable power. It does not rely on solar power. So compared to solar, in particular on Mars, there is a dust storm risk. And so if you have any sort of crewed operations, it increases the overall safety. And then when you actually look at how we can integrate a power reactor within a Martian base or Martian operations, you can have multiple products. Heat and electricity are the top ones, but there are other things that you can do as well. Nuclear power is also one of the things that we are looking at for interplanetary transit. Nuclear rockets, as we will discuss, have some major advantages of going when we're going to Mars. And so this is a technology that we need to seriously consider. To start, the context for what our nuclear options will be on Mars are shaped by what's happening in the commercial nuclear power sector right now. Because of a number of reasons, in part due to limitations in light water reactor technology and Fukushima, there is a massive amount of innovation going on in the United States and abroad. As someone who's dealt with energy issues for years, the pace of this innovation and the breadth of it is really surprising. There are dozens of companies working on different elements of nuclear innovation. This is a map from the think tank Third Way that shows just what's happening in the United States, and this is not even a complete map. There are many different approaches that are trying to do different ways of fission and also fusion power. And so underlying everything that we're looking at doing with nuclear power on Mars or in the future is going to be this commercial innovation, which is also being driven in part by government activities. So to start off, I want to start talking about radioisotope power sources. This is really the workhorse of nuclear energy in outer space. So there have been some those were all in Earth orbit, and those were during the Cold War. Since then, we've not used fission power in space, and we've not used it beyond cislunar space. If we're looking at any sort of interplanetary missions in robotics, we use radioisotope power sources for several reasons. Radioisotopes are a specific type of power source that gets energy from radioactive decay. The amount of energy that you get and the characteristics are determined by the radioisotope. The primary one that we use, and we'll talk a little bit about the fuel cycle issues on, is plutonium-238. And that's because in studies that have looked at thousands of radioisotopes, it has the ideal characteristics. It produces a decent amount of power. It has a good radioactivity profile that you can shield against. And it also has a relatively long half-life of just over 70 years. So when we are looking at doing any sort of Martian rovers or any sort of interplanetary probes, This is the fuel of choice that we use. Radioisotope systems are reliable. We have two main ones that we use, radioisotope heater units. They're very small, about a gram or so of plutonium-238. And that is just to make sure to keep sensitive electronics and other equipment within a spacecraft at high enough temperatures. We also have radioisotope thermoelectric or thermionic generators, which are RTGs. This is really the powerhouse that we use for a lot of our more advanced missions. You can see a picture right here of Curiosity rover. The RTG is the finned white thing on the back side of the rover, up to the upper right. And RTGs are really nice because they are a solid state system, meaning they have high reliability. And so when we deploy one of these, we're not really worried about the power supply as a failure point. Whereas with the Spirit and Opportunity rovers, those were primarily powered by solar power, but they had RHUs to help them with sensitive electronics. But dust storms were an issue and killed one of those rovers because it still was not able to provide enough heat with just an RHU. There are other ways that we can, are other radioisotopes that we can use. Polonium-210 has been used before, but really plutonium-238 is the primary one. And when we start looking at any sort of commercial activities, it's actually not really an option because the supplies of plutonium-238 are very limited. I like to say that's one of the most valuable resources on Earth. And that's actually not true because you cannot possibly buy plutonium-238 right now. Historically, most of the resource was produced as a result of, as a byproduct of nuclear weapons production during the Cold War. And so there is not as much of it now. And because it decays relatively quickly, we have had severe supply problems with that. What we've done in the last several years in the United States is develop a new plutonium-238 supply chain. And that is using a different method. So instead of as a byproduct of weapons production, we actually have our national labs synthesizing plutonium-238 directly. And that is what we have used to create a plutonium-238 supply source for the next several decades. Now, even then, the amount of plutonium-238 that we're producing is on the order of kilograms. There's only going to be enough for some of the planned government missions, such as Dragonfly and some of the other ones that we're looking at. So this is not really an option right now for commercial power on Mars. It does have applications for very specialized rovers, but if we are looking at nuclear power on Mars, especially for any sort of crewed activity, we're talking about fission reactors. So fission space reactors are going to be very different than your grandfather's conventional nuclear reactor, a light water reactor, which is a 1 gigawatt unit. Pictured here is the well-known Kilopower reactor, which would only provide about 1 kilowatt. The Kilopower class is 1 to 10 kilowatts of energy, of electricity specifically. That is not a lot of power if you're looking at a nuclear reactor on Earth, but when you're in space, that's a decent amount of power. And the Kilopower reactor is well known for a number of reasons. It is really interesting because it is the first novel nuclear reactor designed, built, and operated in the United States in decades. Everything else has been a derivation of past technologies. And so that's one of the things that was apparent in the design ethos, the team that was working on this. They wanted to build this reactor as quick as possible. So Kilopower itself is probably not going to fly in space. NASA is currently looking at going to commercial options for a Kilopower class reactor. And that's because the private sector can probably deliver a reactor like this that has similar or even better performance characteristics at a lower price. If we're looking at the current slate of nuclear innovators in the country right now, there are at least 3 companies that are seriously looking at space nuclear power and are going to be considering how to supply NASA. There's at least 3 other reactors that I'm aware of that are potentially space capable, and they could be adapted if the economics were there. And those reactors are actually starting to get into some of the megawatt class range. And a megawatt, when you start talking about any sort of mining operation, is really what you're looking for. And so we're actually at the point now where the commercial industry could supply these reactors in the future. So why do we want to look at nuclear reactors specifically? Really the top 2 reasons are electricity and heat. There are other things that we can do with it and that we would do with it on Earth. Potentially, if you design a reactor the right way, you produce radioisotopes, so it's going to be much more difficult than the alternatives ways. Really, the nice thing about these reactors is that you have electricity and you have heat production. And when you're in a place that's really cold like Mars and you potentially have several different types of industrial processes, a reactor allows you to serve each of those processes. You can also power your base with it. And if you are looking at designing a relatively large system, that's going to have multiple crew and multiple operations, you actually are probably going to want to go for what we use on Earth, which is energy diversity. You're going to want to have a nuclear reactor as well as solar panels. That gives you a fair amount of reliability and also gives you security in case there's any sort of issues, if your reactor goes down or there's a dust storm that disrupts your solar power. Now, I'm not going to talk too much about fusion, but it is worth mentioning. This is a picture of ITER. We are also seeing a fair amount of innovation both at the government level and at the private sector level looking at fusion power. Fusion is relatively difficult to take into space. The technologies that we're looking at for fission are going to be advanced reactor types that we are able to shrink down a lot easier. With fusion power, because you have a lot of complexity and you have a lot of really advanced materials and technology, it's not necessarily a near-term possibility for Mars. We could see a commercial fusion reactor in the world by the 2030s if we're really lucky, but more likely 2040s or 2050s is where we're heading. I do mention this because it is a potential technology option. Now, the fuel is a big issue with a fusion reactor. You have to have, for the deuterium-tritium cycle, you have to have deuterium, which is an isotope of hydrogen, and you also have to have lithium to produce tritium. And so if you were to do any sort of fuel cycle analysis on Mars, you're going to have to figure out how to find those resources for your fusion reactor. Now, I want to talk a little bit about one of the ways we can actually use a nuclear reactor, and that is as a nuclear rocket. So nuclear thermal propulsion is basically just taking a reactor, and instead of using it to produce electricity, you directly use that energy to heat propellant and to use that propellant for thrust. And nuclear rockets are very powerful compared to chemical rockets. Generally, the specific impulse is about twice as much. This right here is an example of the NERVA engine, which was the major nuclear rocket tested by the United States during the Cold War. It had a specific impulse of about 850 seconds. This really was something that we were able to do during the Cold War, in part because we didn't have as significant environmental regulation. The exhaust from NERVA is going to be, or any nuclear rocket, is going to be radioactive. And so you're able to do that previously. That's a bigger challenge nowadays. But we are starting to look at nuclear thermal propulsion today for both our civil and our military applications. NASA and DARPA are looking at similar rocket designs that use what's called high assay low enriched uranium, HALEU. And that would enable us to develop a commercial-based rocket that you could use for NASA missions to Mars. Now, there are major advantages to using a nuclear thermal rocket or also nuclear electric propulsion, which is a nuclear reactor with an ion engine. The primary advantage is that you reduce your overall transit times. And so it might sound counterintuitive, but if you actually have astronauts on a nuclear rocket going to Mars, they're going to get less radiation exposure because their trip's going to be shorter. So even though they have a radioactive unit right behind them, they're going to have less galactic radiation exposure. And so if we're looking at either short-term or longer-term Mars scenarios, and we're looking at transit back and forth, there is a potential argument for saying that most personnel transit might be nuclear powered, just because that does have significant benefits. It also allows you to do different types of mission architectures. So let's go ahead and talk about the fuel cycle. So in order for us to do some of these things, whether that is build these space reactors, build nuclear rockets, or even have a fuel cycle on Mars, we need to understand what the fuel cycle looks like. And I'm going to really focus on the fission fuel cycle as opposed to fusion. And this is a graphic that I helped develop, and this is trying to show the complexity of what's happening with advanced reactors right now. There's a lot of innovation on a number of different items, and there's a bunch of different ways that these reactor vendors are trying to use fuels in a new way. And so when you look at what we're looking for some of these advanced reactors, we need to figure out how to create the fuel supply and make sure that the supply chains are there in order for us to do these technologies. One of the top issues right now, if you're looking at, say, nuclear rockets, NASA and DARPA are looking at HALEU, which you can see is available as part of this right next to enrichment. We actually don't have a system right now to create HALEU on a commercial basis. What HALEU we do expect to make is actually going to come from government stock, so we're going to downblend it from highly enriched uranium. And if we really want to unlock the ability to build these space reactors, to build these nuclear rockets, we need to figure out how to get that HALEU commercial supply chain in place. That's something that we're starting to prioritize right now because there are a lot of other reactors on Earth that are for terrestrial purposes that use HALEU or want to use HALEU. But we need to make sure that that timing works out well, particularly when you're considering how the timing of any sort of Mars mission or any sort of nuclear rocket testing would play together with having availability of fuels. We're going to go through a little bit more about the fission cycle in detail. But first, I want to talk very briefly about the fusion cycle. So if we ever get to the point where we can actually have a fusion system, either for fusion propulsion or a fusion system on Mars itself, the fuel is going to be a little bit of an issue compared to uranium. And that's because we're going to have to process a relatively large amount of water ice on Mars to actually get that fuel. There are other fuel cycles like helium-3 that we could use that are much further down the line. But realistically, anything in the future is going to be deuterium and tritium. And those reactors are going to be relatively hard to deliver, and we'll have to figure out the fuel for them. It's definitely an option, but if you're looking at what we're probably going to do in, say, the next several decades or by the end of the century, it's still most likely going to be fission. And actually doing a fusion fuel cycle on Mars is going to be potentially more difficult than uranium or even thorium. Let's go ahead and talk about how we would take part of the fuel cycle and put it on Mars. So when we look at the front end of the fuel cycle, there's one more step in here besides the 4 on the screen, milling, but we're talking about mining, conversion, enrichment, and fuel fabrication. This is a relatively complex process, and for a number of reasons that I'll lay out, I think it's unlikely that we would want to replicate this on Mars anytime soon. To start off, do we know whether there are nuclear resources like uranium and thorium on Mars? Yes. We don't know how much there is. We don't necessarily know where the ores are. We don't know what mining systems would look like other than they would vaguely resemble what we do on Earth. But we do know that they do have resources. The graphics here are maps from an interesting presentation that compares the surface readings of potassium and thorium on Mars with what we have from Martian meteorites, which are subsurface samples. And based on the difference that these readings are have much higher concentrations, the paper posited an idea that at one point in the past, there was a natural nuclear reactor on Mars that ended up causing a big explosion and distributed the nuclear materials across the planet. So there are nuclear materials in the soil. It's probably not going to be anywhere near enough to actually mine and process that. You'd still probably have to find an ore. And we still don't know enough necessarily about the geology of Mars to be able to identify those ores, but this is a good evidence that they're potentially there. When we get to mining, though, because of how uranium particularly works, when we look at uranium, only less than 1% of it's uranium-235, which is fissile. So to get to that uranium in the first place, you have to mine a lot of materials, and then you have to go from that uranium that is 1% or less, 235, to be able to get to a usable fuel. So this just shows a table of the top 10 uranium mines in the world. And so nuclear power is 10% of global electricity. It's a lot of energy, but these 10 mines are providing 55% of the total uranium needs in the world. It's a relatively concentrated industry, and the amount of effort that you would have to do to actually make the mining portion economic is going to be really high compared to the potential uranium demand you would have on Mars. Similarly, there are only a limited number of conversion facilities in the world. So once you've mined the raw uranium, you need to convert it chemically so that you can use it and process it into fuel. And so the conversion level, again, are a limited number of facilities. It's not necessarily clear. You could definitely miniaturize this, but at a certain point, it's not going to make sense to do the substantial amount of mining and then conversion, and then next, which is enrichment. Enrichment, these are all the facilities in the world. It's really small. If you look at how the enrichment and the uranium flows work around the world, there's only so much enrichment working on the commercial side. And to build all of this and then get to the final point, fuel fabrication, you're already developing a pretty substantial amount of infrastructure on the front end. And then fuel fabrication is where things get difficult. On the right side of the screen, you can see a traditional fuel rod structure for nuclear power. That's for a light water reactor. We're probably not going to be using light water reactors on Mars. You maybe could, but I really don't think it would make sense. I would be questioning what you're doing. What we are going to be likely to use is potentially the things on the left side. So on the upper left, we have TRISO, which is, they've been called power balls. They're essentially self-contained small nuclear reactors that you put a ton of them together. It's a really accident-tolerant fuel. It has essentially self-containment. That's one of the things that people are looking at significantly right now for potentially space applications. On the bottom left, we have a molten salt reactor where the fuel is actually in a molten salt. So once you've done all those front-end processes to finally get to a enriched amount of uranium that then process it into fuel, you potentially have a number of different reactors or reactor types that you're serving on Mars, and each of those are going to require different fuel facilities. So the point of all this is that when you look at all of the things that you would have to do on the front end to get to a finished fuel product, it's probably not going to make sense, even in the relatively long term, because the amount on a mass basis of fuel that you actually need is relatively small. And so if we start talking about long-term scenarios of interplanetary trade, you're going to want to be trading things that have the highest economic value per mass, and nuclear fuels clearly fall into that area. It's going to be much cheaper to do all these things on Earth, where you have a lot of other nuclear production going on anyways. You have some political concerns potentially about launching, but that can be addressed in a political manner and with safety and technical considerations. But it doesn't make as much sense to do things on Mars for the front end. That said, though, when we actually look at some of the other technologies we're developing right now for the rest of the fuel cycle, it could make sense to build a reactor on Mars. And one of the things that we're doing right now in the United States is a number of different applications with additive manufacturing. Currently, there's a project called the Transformational Challenge Reactor, which is actually 3D printing a nuclear reactor core. And with that, it's going to use TRISO, so you can just put the fuel right in there and then run a reactor. So it's possible that you could build the reactor and parts and everything else that you need on Mars. And so the only thing that you would be importing for this type of fuel cycle would just be the fuel. That said, when we start getting to the back end of the fuel cycle, you get into an area where there could be a fair bit more political controversy. So when you actually are done with a reactor, you're going to have to decommission the reactor itself. You're going to have nuclear waste to deal with. Some of it's going to be the really nasty high-level stuff. And what we've done historically with nuclear reactors in space, we put them all in graveyard orbits, which has not really worked out well for the near-Earth environment. One of the major satellite collisions was a decommissioned Soviet nuclear reactor. But when we actually look at what we do with RTGs, we just have them decommissioned and waste storage in situ. And that makes sense because over time that radioisotope will decay. That unit won't be radioactive and dangerous in, say, 100 or 200 or 300 years, whereas the high-level waste from a fission reactor is going to be much more worrisome for a longer time. One of the nice things, though, that is about Mars is that because it doesn't have anywhere near the water cycle that we have on Earth, a geological waste repository is very feasible. So it is technically feasible on Earth. It is largely a political concern. But when you actually look at places that you can put it on Mars, you can dig it, put it in a place, and be relatively certain it's going to stay there geologically. You just have to figure out how to get political permission for that, which could be an issue. Finally, because of the very high value of any nuclear materials you have, there is a good case for nuclear reprocessing, particularly if you do have to import this fuel from Earth itself. There are going to be some concerns about the process and whether it's going to be economic if you do have different types of fuel forms. But if you are able to do this in the right way, you could have a reprocessing system on Mars that would allow you to use a lot more of that fuel domestically and make the overall fuel cycle closed to a certain degree on Mars itself. The problem, and this is a problem generally when you look at taking any sort of fuel cycles off world, is nonproliferation. Enrichment and reprocessing are the main points that nuclear power intersects with nuclear weapons. And because of the Nuclear Nonproliferation Treaty and the Outer Space Treaty, you are not allowed to build a nuclear weapon on Mars. I really hope you don't nuke Mars or anything like that. But when we actually start applying this to space reactors, what we've seen the main pushback on nonproliferation issues lately has been the use of highly enriched uranium. So Kilopower was a highly enriched uranium fueled unit. And one of the reasons I think that the NASA is looking at commercial entities for LEU or HALEU designs is to avoid any controversy on the nonproliferation side. The nonproliferation community was relatively worried about NASA doing that because US policy is to discourage the use of HEU for any sort of civil application. Long term, if we do have a lot of nuclear material in space, we might have to have safeguards and monitoring. And that's just to make sure there isn't sort of any clandestine weapons programs. We could probably develop the tools to do that, though. So I'm almost done
Alex?
on time here. Yeah.
Yeah, sorry, just 1 minute to wrap up to start the Q&A.
Perfect. Well, last slide. So in light of all this, taking a step back from Mars itself, there's been a number of interesting and exciting space nuclear developments lately. Last year, the administration released a new launch memorandum that outlined a commercial pathway for the first time. It's still a really complex regulatory way to do things to get a nuclear reactor launched if you're a commercial entity, and there's a lot of uncertainty involved. So eventually we're going to have to figure out some sort of regulatory solution, but there is a fair amount of movement that's going on in this. One final point that is important, we need to figure out the role of the NRC, the Nuclear Regulatory Commission. They do regulate nuclear materials and reactors. It's not clear what their role would be once you launch the reactor into space. So thank you for this presentation. I hope it's for joining this presentation. I hope it's been helpful, and I look forward to the Q&A.
Awesome, thank you so much. We have 2 questions so far in the chat right now. One question is from Alexander Goinis asking, if feasible, fusion power is discovered and created between now and the time of permanent Mars settlement, would it be feasible to transport it to Mars?
So yes, that's a really good question. Where we are in fusion right now is still an area of high technical uncertainty. We're probably going to be able to create net energy fusion within 10 to 15 years. It could be potentially sooner depending on how things work out. Getting to the point where it's actually a economic and functional reactor at a commercial level is going to be much more of a challenge. In terms of building the reactor and transporting it to Mars, it's going to be a really big mass issue. So with a nuclear reactor, for a fission reactor, a lot of that is actually relatively simple when you compare it to a fusion reactor. Most fusion designs that we're looking at right now are going to require a fair amount of cryogenics as well as magnets. And to build all of that and put it into a small package that we could then send to Mars, it's going to be a really big challenge. Whereas we have established the fission reactors right now. It's certainly possible, but I'm not necessarily sure there's a clear rationale that you'd want to prioritize that, at least in the near term. And there's also a fuels issue, trying to figure out the fusion fuels in the longer term.
Another question from Leonard Lopin is asking, which nuclear startup is currently working on the smallest modulator reactor that might be used on Mars?
Ooh, that's a good question. So in terms of the small ones right now, I know that BWXT, X Energy, Atomos, and I'm missing someone that's definitely doing stuff. UNSC are all looking at space applications right now, or near-term applications for nuclear reactors. There's also a number of other reactors that could apply. One that is really notable is Oklo. That is a fast reactor that is the first company to apply for a non-light water reactor to the Nuclear Regulatory Commission. That's really interesting. They're not really intending to use it as a space reactor right now, but their potential design is very similar to Kilopower, and so they could actually adapt that to a space reactor under the right circumstances. So really what we're looking at right now for most of those designs is probably going to be in the 1 megawatt range, maybe a little bit bigger. And I think I'll be really interested to see what happens with the NASA solicitation for a commercial Kilopower replacement, because NASA's only asking for 10 kilowatts. Some of those designers actually might go a lot higher.
And one more question we have from Helen Mattinson is if there are any concerns about crew safety for an onboard RTG.
So good question. An RTG, you are not going to have that much radiation, and it's largely going to be shielded. So there's the famous scene from The Martian where you have Matt Damon holding the RTG to keep warm and like talking about how he's worried like there could be radiation exposure. He's almost certainly getting more radiation exposure from being on the surface of Mars than being next to the RTG. The RTG is not that much, and one of the reasons that we prefer plutonium-238 is that the shielding requirements are a lot lower than some of the other radioisotopes. But it's a fair concern. It's a bigger concern potentially with space reactors, and a lot of the design for a space reactor is going to revolve around how do you do shielding in the right way, particularly for a nuclear rocket.
All right, awesome. Thank you so much for joining us, Alex.
Yeah, thanks
It's
everyone.
a real pleasure to have you at the conference. And that concludes this meeting.